the last class was all about 1D Ising model, which we now have to finish. So just recall one or two things and then move on to the next, another bit about the 1D Ising before finishing it off. What we said was last time that I have this long chain, and what we did was that there was this Z for n particles which had to be evaluated, and what we decided that this was a sum over all spins e to the power beta j si plus 1. So sum over all configurations, and sum over I over here. And what we said that let's break it up, break up this evaluation into step-by-step processes, where the first step is do integration over all odd spins, for example. So if I call this beta j some k or whatever, k is because j, the action really lies in the beta, and so it is some k si plus 1, and that goes to a sum over remaining spins and e to the power some k prime and summation si plus 1, except that this was I equal to 1 to n, and now the 1, 3 and so on are gone, and you are summing over I equal to 2, 4, 6, 8 and so on. But the interesting thing is with this one-dimensional model that the form has been preserved. It was si plus 1, and I still have si plus 1. That is the secret behind why it was exactly doable. That is, all the answers that we got from here were exactly right. That is, what is exactly right? Exactly right is the fact that we got the correlation as going like e to the power 2 beta j. So this is it's the correlation length of the susceptibility which would be important. The susceptibility proportional to e to the power 2 beta j, the correlation length going like this, and the whole idea was that I got k prime equal to some f of k, and I looked at the fixed point k star of this transformation and argued that, and that this part is just maths. Now comes this, and you want to relate the k star to criticality. That was the key issue, that if k is equal to k star plus delta k. If I start with recursion, so let me make this, I mean, kn plus 1, kn. So that's the k at the end, it makes it somewhat easier. And each of these corresponds to xi at the nth becoming smaller by a factor of 2, because it is from, so lattice spacing has been doubled, and unit of length is the lattice spacing. So I move away a little bit, and if this is what happens is, I found that this, if I move away a little bit, then you move away a little bit more. So if kn is delta k away from k star, then kn plus 1 is further away. Yeah, so you go away more and more away from criticality. Criticality is a question of interactions and strong interactions, and as you are going away, the interactions are strong because they are closely spaced. Let's say nearest neighbor interaction, and then you are going further and then finally reduced to 2 spins. Just don't have to keep track of easily doable, straightforward partition function. So you go away from, so this fixed point that you talked about, this fixed point is an unstable fixed point. So criticality is associated with the unstable fixed point. If you go away, if you go away along the, now what determines this k over here that we talked about is like the temperature. So temperature decides criticality. It is Tc. Tc in this case we have known from previous is Tc equal to 0. So the fixed point which corresponds to this Tc equal to 0, this coupling constant determined by T, which is J over Kt, the fixed point is infinity, K star. So K star is equal to infinity, and it's an unstable fixed point. That is, if I am slightly away from it and I iterate, if I'm on it, I'm there for all time. And that's what fixed points are. I mean, it's K star equal to f of K star. But if you are away from it, you go more and more away from it. That's an unstable fixed point. So if I had, this is something which you can try out for yourself, that if I had an additional coupling constant, additional term, which is an external field, Si, then when I change this, the H would go to a H prime under this, I mean, that is Hn to Hn plus 1. And the point would be that H star would also be equal to, the fixed point would be this K star equal to infinity and H star equal to 0. Once again, so the fixed point is going to be K star H star, which would be infinity and 0. And it would be, I mean, so here at the origin, and whichever direction you go away from, and that is, if you start somewhere over here, you are driven out. If you start somewhere over here, you are driven out. So both K and H are variables in which, so basically in this KH plane, wherever I start, I will be driven out. But suppose you did something what about putting in next nearest neighbor spins? Yeah, go ahead. H equal to 0, just as T equal to 0, the fixed point is T equal to 0 or H equal to 0. The criticality is determined by TC, TC equal to 0 or H equal to 0. So in a finite field, the critical point is determined by these two variables. হ্যাঁ, so দুটোই আমাকে ক্রিটিক্যাল ভ্যালুতে থাকতে হবে, and so that if I am at Tc equal to 0 because but I have a finite magnetic field, তাহলে the you are not going to see a critical behavior. So finite H at Tc equal to 0 is not critical. And similarly, at H equal to 0, a finite T is not critical. It is only if you tune it to H equal to 0 or K equal to right. Thank you. So K inverse, and so this, which corresponds to T equal to infinity and H equal to 0, that is the critical point. It is also, this is what you can very easily check, that it is unstable in the H direction as well. That is, if I set something over here, it will go away. If I start out here, it will go away. If I start out here, it will go away. So start out anywhere on this plane except at the origin, things are going to go away. Huh? If you imagine that I introduce other coupling constants. For example, I can introduce a next nearest neighbor coupling. The next nearest neighbor coupling has no effect, in which, if you do it, would be seen by the fact that the recursion relation there would drive it to 0. Huh? This is with the 1D Ising, that's why it's popular. You can play a lot of games. I can easily switch on the H and check for, because after all, I mean, this term is easier than this. Huh. So it is but let's say I have a next nearest neighbor interaction. That's not so easy anymore. But if you carry out the, for example, the renormalization group argument can still be done, particularly if I next nearest neighbor would put in 1 and 3, 2 and 4. So I remove, I remove 1 and 2. I would be generating some coupling which would be between, so I would be removing 1, 3, and so on. I would be generating some other coupling between S, whichever is a survivor. S1 is gone, S3 is gone, S5 is gone. So with S2, there would be a coupling at S6. So in S2X, so there would be a S2S6 coupling with a coefficient. And that, I mean, whatever the old coefficient was, you would be able to relate that. What I'm saying is this, that if I started with beta S1, S2 plus S2, S3 and so on, times e to the power, let's say some beta 1, and this is S1, S3 plus S3, S5 and so on. So no, this is, sorry, it is beta J, this is beta J1, and the coupling goes like this. So I call this K, I call this K1. And I do this tracing business, which removed S2, which got rid of the S1, S3, all the odd ones. So S1 and S3 would be gone, this would be gone. You would find that you would be ending up with something which looks like all the odd ones gone, and I would be left with S2 coming up with S6 over here. All the odd chaps are going to go, so this is going to go. This is going to go away because I'm going to trace over S1, S3, and so on. So S5 would be S5 would be a player, and then S5, but S5 is gone. So what would be the next generator that I would be picking up? My survivor is S3 is trashed over it is S1 S3 plus S2 S4 plus S3 S5 and so on, and I'm tracing over the alternate spins, and I would be left with your S2 S4 S4 S6, though they are not traced over. You would find, so what's going to happen? So S2, this is traced out completely, S1, S3 is traced out, this is traced out, and you are going to get all that is going to happen is that you will get S2, S4, S4, S6, they would be unchanged and the same coupling constant holds. So the same coupling constant holds, and the next time around when it is the you are going to get rid of alternate. So let's see what happens. 2, 3, 4. So 1, 2, 3, 4, 5, 6. I have got rid of, let's say, let's put a 0 here. 1, I have got rid of 3, I have got rid of 3. I have a coupling which is nearest neighbor, and then there is a next nearest neighbor, that is, there is a coupling like 1, 3. At this stage, I still get, I'm going to end up with 0. So 0, 2, 4, 6, 8. And as we saw last time, that it is the removal of S2. Sorry, that's not what we did. Let's say we removed 2 and we generated this. We removed 2, 4, 6. So if 2, 4, 6 are gone, then it is 1, 3, 5, 7, 9. So these are left. And between these two, I have picked up the coefficient which came from here became something different. But now what comes from the S3 it is S1 S3, but S1 S3 which was there before, that remains unchanged. So the transformation that we did had no effect on at that stage, has no effect on this 1 and 3. But if I go next step over here, I have this 1 and 3 and the 5 and 7. And what has happened is that now this 1 and 3 will lead to a coupling between the 3 and the 7 and so on. And what the coupling that I had before, the S2, S4 and so on, is irrelevant because it's as good as starting out with 0. Right? I mean, if I had a term, for example, if I had a second nearest neighbor term and we went and did this over here, at the next stage of this decimation, you would see that I'm left with 1, 3, 3, 5, 5, 7, and so on. Now, the point is that with 1, 3, 3, 5, 5, 7, I have the old answer, And as for the what happened to the previous, that is, you started, if I started out with a e to the power k1 s3 s5, then that is not, that is simply not going to be altered. This process completely, I mean, bypasses. So this coupling constant is unaffected by what went on over here. But now what has happened is I have a new coupling constant which is generated out of this 1335, which is, and so at this stage what becomes is that this k1 simply becomes a part of it. The k over here, the k has become a k prime s3 s5, right? The k has become a k prime s3 s5, and then k prime. So what this is contributing to is that k1 at this stage, it is k prime plus k1 defining a new, let's say, k forever for me, and then it is just the Ising model that we started out with, because now you go ahead and take this and set up the recursion relation. And therefore, whatever the two-spin coupling, that is, so long it is as it is a two-spin coupling, and but not nearest neighbor something else, it is not going to play any role in what we have discussed. You would have to go to a higher order spin coupling like S1, S2, S3, S4 to actually see the what kind of an effect. So if I change this by a next nearest neighbor coupling or a next nearest neighbor coupling, at some point it will just reduce to the one-dimensional model. Right. So S1 এর উপর ট্রেস হয় সেটা S2 মানে S2 এর উপরে যদি ট্রেস করি তাহলে পরে ওটা S1 S3 হয়ে যাবে। হ্যাঁ, আর এটার কিছু হলো না। S2 S4 traced হয়ে গেল, so that number becomes a constant, right? মানে e to the power S2 S4 summed over S2 equal to plus minus 1 and S4 equal to plus minus 1 is simply going, প্রথমে S2 টা করে নাও, e to the right, so ওটা just একটা নাম্বার হয়ে গেল। হ্যাঁ, তারপরে ওইটা হয়ে গেল। So তাহলে with a two next nearest neighbor or next I don't change things. But if I have a four spin interaction, tahole pare it is going to change, but the point would be je sheita hole pare you would find je unlike the fixed points that you get over here, which are unstable fixed points, or fixed pointer would be a stable fixed point. Right.
তো আমি নেক্সট নেবার নেক্সট আপনার কোর্স স্পিড নেবার এখানে একটা ডিরেকশনে এগেইনস্ট তো আপনার মানে স্টেবল রেসপন্স হবে, আরেকটা ডিরেকশনে
মানে এইটা will remain sure, yes, right, but the other directions which I introduce, সেই direction গুলোতে it will all be stable. Acha, all right, if you yes, right, okay, sure. When any other coupling that I have apart from eta or eta, they would correspond to some stable the fixed point in this huge space of, let's say, K1, K2, K3, and so on, would have, as you said, different axis, a large space, but stable along only two, unstable along only two directions, TC and H, stable along everybody else. So if it has to go away from the fixed point, it must have a component when it has to move. The initial condition has to be has to involve movement away from this condition. সেটা করে দেখতে হবে, সেটা obviously করে দেখতে হবে, yeah, with a we will see, I mean, with the Ginzburg-Landau, the argument is far more trivial, because I can do it simply by power counting. Over here, the argument is little more complicated. As you see, I would actually, if I had a 4-spin coupling like S1, S2, S3, S4, I would actually have to figure out why, with some calculation, an argument why its prefactor would have to, at the next round, become something which is smaller. And so eventually would have to go to 0. So the point about raising this issue over here was that variables for which, I mean, in general, nobody, if I have a realistic system, the realistic system is not your Ising model. Now, you give me any system in this world, and it is certainly not going to be, Ising would be an approximation in which you keep the next, in which you keep the nearest neighbor, and but the reality, if I have a real material, it will say, you have to get there is a next nearest neighbor coupling, there is a next to next nearest neighbor coupling, and some of them could appear to be big. I mean, that it's not all that small. How do you get rid of it? Or there is 4-point coupling, there is 4 spins interacting among themselves, or 3 spins in. So why are you in? The point with what the renormalization group stress is that yes, in the group, the recursion relation has to be constructed in the large parameter space. That is, you give me a starting, you see, you give me a starting Hamiltonian which says it is J Si plus 1, then it is J1 Si, let's say Si plus 2, and similar ones over here. Then it is K1 Si plus 1, Si plus 2, and a class of these. And then a class of, let's say if I have up-down symmetry, not a, let's rule out the by up-down symmetry, the odd ones. So Si plus 1, Si plus 2, Si plus 3, and so let's focus on this. Who tells me that this is unimportant? What I need to do is that over here, I said that if there are terms like these, they are just going to fall into this. So they are not, in this particular case, they are not all that. In principle, there is no difference between this chap and this chap. But
we are in scale very invariant region. Therefore, the correlation between therefore this neighboring ideas of neighbors are
no, it is like the point is that so long as it is in this case a two-spin interaction, if I said that this and this differ only by the lattice spacing changing, the nature of the coupling is not different. No, it is just the lattice spacing which has changed, and therefore after a few steps of elimination, this is going to look like this. না মানে এইগুলো তো সবই renormalization প্রসেসটা ল্যাটিস স্পেসিংটা চেঞ্জ করছে, রাইট? সো ও কয়েক স্টেপ পরে ওর মতন দেখতে হয়ে যাবে, কারণ অল দ্যাট ডিফার্স ওভার হিয়ার ইজ আ ল্যাটিস স্পেস। হ্যাঁ, কিন্তু এর হবে this point, right? So this is going to go to some k1 prime, and whatever is left after the tracing over, but it would have to be a 4-spin business. And the point is that when this goes to some k1 prime, so that suppose I have just one, then it is I have a 3-dimensional space, that there is this k1 here, there is this k, and there is a h, right? And the fixed point, let's say, is, I know that as you said, let's put a k inverse. The fixed point is in this k inverse, and let's say the fixed point for k1 is 0. Or anyway, let's say it is 0. If I move, if I start out here, I'm going to go away. If I start out here, I'm going to go away. If I start out here and go away, I'm in trouble. So all the arguments that I gave, I did not do the h, but I assume that h equal to 0 would be the trouble in the sense that if this is going to be such that you can become critical along this direction, then I have to worry about what effect it would have on the exponents that I get over here. It's a new critical point. This system is the one which we were doing naturally is determined by the temperature and age. You are making a statement that everything else is unimportant, right? So what is the meaning of that statement? What is the meaning of that statement is that suppose I have this k1 which and now let's say I have a fixed point which is k1 equal to 0. Is k1 equal to 0 and important? Now what makes it important and what makes it unimportant? The important business was that the picture of important was that the correlation length over here, this is the criticality. So criticality correlation length was xi equal to infinity. So if I start out here, I have to go away from because the process of this is to make the system more and more, I mean, decrease the correlation length in terms of the lattice spacing, and I go away along. And similarly over here, I would have to go away. If that happened over here, then I'm in trouble.
That means you cannot drop that term.
Then I cannot drop that term. But if it is stable in this direction, that is, if I start out here and it goes here, then I don't have to worry. It is the unstable fixed point which corresponds to xi equal to infinity. A stable fixed point will not correspond to xi equal to infinity. So the all this, the relevant, irrelevant, is the these which give you a unstable direction, the unstable manifold of this fixed point. I mean, if I have a large number of coupling constants and a large space, then it is the unstable manifold which has to do with criticality. Because everywhere along that direction, if I move away, then I move away from criticality, which is the renormalization group picture of criticality.
Can be made because of the density of. So over here, does that this constant, does it depend on the density or
No, that kind, see, that is the that kind of argument which I gave for the Ginsburg is restricted to that class C, because I could make a statement about this that ddx and everything I have. Once I have this, I always have the freedom of calling this one and fixing phi, and thereafter I know the dimensionality of each of these, and a priori I can just by power counting just say that what will grow and what will not grow. No, so this feature I don't really have over here. I mean, a priori, by looking at it, I can't really tell you that it is, I mean, the dimension of K1 is not, because, I mean, these spins don't have a dimension. I mean, I had this freedom, this gives you that one of the advantages of using a continuum description, that you put it like this, and
what about the other way? If let's say we are dropping a term from an angle, so does that mean that coupling term corresponds to a point?
And see, the point is the dimension in this. If it is it's kind of difficult, because the point is that the couplings which we talked about were like, what kind of a coupling is this? Si plus 1 is like Si minus Si plus 1, and therefore it is like a gradient coupling. And Si plus 1 is like a gradient coupling, because this is Si minus Si plus 1 whole square, right? I mean, this is half Si minus whole square minus half minus 1, right? That is Si plus 1. Now this is the difference at two different lattice points. So that is like a gradient, right? So this term is really like, I mean, essentially this term over here. Now all right, I mean, this is now if I look at this term over here, you can sort of say that this is like a higher order, that these two correspond to a gradient, this two correspond to a gradient, and therefore it is like del square, and del square is irrelevant, and therefore this will be irrelevant. So that's a possible way of thinking. Yeah, but right, I mean, how accurate this is, I really, I mean, going from these discrete differences to gradients and so on are a bit complicated, so the reasoning has to be a little more, but certainly, I mean, this is, I know that this is irrelevant. I also know the power counting that we did told us that del square, I mean, this is phi del square phi, this is all right, but if I had another del square, I mean, if I were to look at del square phi, phi square, del square phi square, then it would not be that's neither would del square phi whole square be there, or neither would phi square, and also I think that phi square grad phi square, that also would not be a but over here what are we looking at is sort of like, I mean, you know, it is like grad phi times this is a grad phi, and you can call this another grad phi, and have it as a square. No, si plus 1 is 1 minus this, so you say this thing is like a grad phi square, and this thing is again like a grad. So this is like a grad phi square, this is like a grad phi square, and hence this has hence it's irrelevant. If I were to, that is, if I were to translate this to the Ginzburg-Landau kind of argument, then I would say that this is like this cup is like as I say, if you cast it like this, then it is like a grad phi square, and then this is also like a grad phi square. Now, is that a rigorous argument? Certainly not. But in this case, if I give you that argument and said that, look, that is why this is irrelevant, yeah, it works. This is
the whole idea of normalization. So, build up on the fact that we are working in a discrete system, or it also holds for the continuous.
I mean, primarily discrete system is actually allows you to visualize very, yeah, all right. The process which we have followed over here all right. So what the process which we have done over here is renormalization in the, not in the field theoretic sense, It is I mean, this one has to be very careful about that. What we have done over here was we simply said that if I were to remove these, I, I simply mapped this to another problem which looked like a beta j prime and si and si plus 2. So I simply mapped it to this problem over here and said that, all right, this is how the, so if this is k prime is some function of k, and this process of, I call this a renormalization because essentially what you are doing is carrying out, you are writing down another effective coupling constant after you have removed this. So it is more like effective from this to another theory which looks like this but with a different coupling constant, and I use the word which is a different coupling constant and call it renormalization because the field theory which came in the 40s and 50s called these coupling constants. You say I were to do QED and I have the Dirac part, I have the EM part, and all these are linear. Here is some psi bar psi, here is some A, and then you have psi bar A psi. Your coupling between the electromagnetic and the. So for this, I mean, this is quadratic. One knows, and this was the problem because as soon as you started working with this, it started giving you terms which change the coefficient over here. It you work out this diagrammatic. This is a vertex which looks like this. These are the psi lines, and this is the A line, and you have two such vertices, and you pick up the first non-trivial diagram which you have over here, and which you think is, I mean, the photon propagator would have looked like this. This is like a photon propagator and with a insertion over here. So you call it the renormalized photon propagator. So the word renormalization comes from there, and this blows up, right? And then the point is, so this, what was a renormalization, renormalized propagator that blew up, and therefore the point is, you had to quote unquote renormalize the theory so that this actually you had a way of removing the infinities. So the process of removing the infinities came to be known as renormalization. And later people, so that was, well, whatever, I mean, this technology nomenclature, but this, so far as the early Feynman showing, it was the renormalization was the process of removing the infinities from diagrams like this. Later people were essentially gave the, I mean, when condensed matter, that this is a, we are talking about renormalized propagator over here, just as there would be diagrams which would be, I mean, this interaction would also change this propagate. I have a psi bar line over here. The psi bar line gets affected because this goes to, I mean, this can go like this, and then this can, or this can form like, and there can be a this kind of an insertion. So this kind of an insertion would be, this was the mass term over here, so it would be changing the mass over here. So you call, and that correction once again was infinity, and therefore you had this. So this was going to change the coupling over here and make it the charge go to infinity. This would make the, and therefore you had to do, I mean, you set up a process which made it feasible to remove the infinities and talk about the in a consistent manner. And so that was the, but since this was a picturesque word, that the mass that you start, you imagine that you start with a bare mass in the theory, and then you sort of get, and then the contribution that you get, finite contribution that you pick up from here is going to go in there and give you the real mass and so on and so forth. The real mass is the renormalized mass where all such things have been taken into account. So this the word renormalization is a little over here in the is the when things settled down. I mean, everybody started speaking the same language. That over here you say that the mass changes from scale to scale, and that has a flow. The coupling constant changes, that has a flow. And over here you are also saying the same thing, that it is a question, but this is entirely within the field theory. This is, so QED is a purely field theory one never, but here it was an Ising model, mind you, to start with. Ising model, and therefore, so there was the Ising type of thing, and then there was the Landau-Ginzburg. And you look at the two a little differently, in the sense that here it is this e to the power beta j si sj summed over, and then sum over configurations. Over here, partition function, which is like e to the power minus half grad phi square plus half grad phi square plus some lambda 4 phi 4. Yeah. So over, so there was this. There is this starting point. There is this starting point. Now, over here, the renormalization process that we have been talking about is a question of doing a part of the sort of setting up a scheme by which you remove some degrees of freedom and start talking about different system which looks like here this, but in the process you could be picking up the, we were lucky, we didn't pick up any 4-point interaction. A few days later when we tried the 2D, we will be picking them up. So this process can generate new coupling constants, and you have to make sure that they are not going to spoil things for you. And therefore the whole business of this formulation is really that I start with not just SISJ, I have a SISJ SK, SISJ SK SL, and that is the complete story. And then I do this process over here, and it is only one process which would give me, I mean, only one coupling constant in the zero field case, which would become infinitely big. I mean, which would be essentially corresponding to an infinite correlation length, and it would be an unstable fixed point. Because how would you recognize who is the infinite correlation function chap? Now, which is the fixed point which is unstable? Yeah, because the argument that we gave, that part is correct. Yeah, that if I'm away from it, the process of renormalization, the process that we have done is simply eliminate degrees of freedom. So that, as such, nothing to do with the renormalization that was done in the 40s and 50s. They simply there it was. I mean, as I said, the QED do it all in the continuum, nothing to worry. I mean, it has its own language. Over here, why am I borrowing that language? It's borrowed simply because that if I think of I know the process here. The process is that I have this large number, and I know that I do this decimation process. I get a fixed point which corresponds to infinitely big correlation length, and therefore the fixed point of this has to be unstable, the relevant fixed point. And after that, you will look at which are the things where which are the directions in which you will go away from the fixed point. Those are the ones which you need to control. The others move into the fixed point, you can ignore them. So that relevant and irrelevant. Over here, the game is different. Over here, the game is different. This is like the standard field theory game. That here you are, that you have to calculate, for example, a physical quantity, namely the susceptibility, for example, or which is the correlation function. So physical quantities are the correlation function. I carry out, without this, I know I have a finite answer. I start a perturbation theory in this, that's the next thing to do, and I have a divergence. So that makes it, and now I must have a scheme for controlling that divergence. All right. So now this, therefore, has to be very similar to the QED that I talked about. So QED was the same. I mean, you have so long as I don't have the electron photon coupling, life is trivial. As soon as I have that, then I construct diagrams which seems to change the electron mass, which affects the electron photon coupling. So those diagrams blew up, but the blow up was for large momentum. The blow up here is at small momentum. So it's a large distance phenomena. The blow up is at small momentum, and the rules are. But yes, right. It's the word renormalization is very relevant, because it is the you try to as soon as we calculated the G, which was 1 over, in K space, 1 over K square plus A. So G inverse is K square plus A, and now a few days later we will be calculating the contribution to G coming from over here, and that the first correction is going to diverge. So that is going to diverge just as QED diverged, and except that now I have to get a new set of a different set of ways for making things finite, because this divergence comes in a different region of space. Yeah. So all right, but in principle, the diagrammatics that you do over here and the diagrammatics that you do in any QFT are actually the same. I mean, it is, the rules are the same, everything remains the same, but you are looking at different range of the length scale. Over there, you are worried about the high momentum. Here, you are worried about the, but the task involved remains the same, and therefore that goes by renormalization. This goes by renormalization, and you know, but there is a yeah, right. I mean, that's where the similarity and the differences lie. This, it is technically the QED on a lattice probably has an analog of this, which all right. Certainly the lattice gauge theories, which were I mean, that part of have an that has analog to this. They came interestingly a little later, because it was all field theoretic till the mid 70s or late 70s. And then when the computing power became high, that's when one could take a QED and put it on a lattice. Also, the strong coupling, the various kinds of gauge theories with had problems in the continuum, which the lattice people could sort out. But anyway, I mean, but over here it is the lattice which came naturally. I mean, Ising started, yeah, Ising, as he was given a PhD problem, yeah. So and the Onsaga and so on. So Ising model over here was the driver, and then superconductivity brought in the Landau-Ginzburg business. So there was this, and eventually the Landau mean field theory was essentially based on this, but was not pushed very far beyond that. But then the 70s sort of brought this and this together, and the high energy followed in the next decade. That, all right, I mean, it's the same game, this at long wavelengths. Sure. Yeah. So that is the way it goes. So what we essentially have done so far is simply that, look, I mean, over here, if I take a 1D Ising model, I get the language, this language which is coming in was not there in the critical pre-RG days. What you are saying is, look, I mean, what we wrote down was that this coupling constant, and this is where I mean, this is why the critical phenomena was very important for everybody. What we said, that Jn plus 1 is f of Jn. That is, the J changes, and what changes an iteration? What are you doing? What is meant by iteration? You are taking a lattice where the lattice spacing is A and changing it to a lattice spacing which is 2A. And so in the that is, I mean, so this is the nth step, this is the n plus 1th step. The lattice spacing has changed by a factor of 2, and at this stage this is this and this. Imagine that I do this not, I mean, on a lattice you have to think of changing lattice space by integers. If this is a continuum, then I just say A goes to A plus delta A. Yeah. So if this was a theory set on a continuum, then instead of this, you would have a dGdA. That is the flow of the, so the unifying language which was going to come is this, when put in the Landau-Ginzburg form, as you will see, will automatically say that the coupling constants flow. Over here, I am saying that by every time I remove a set of spins, coupling constant changes, which is equivalent to saying that I have made the lattice spacing bigger and therefore the coupling constant has changed. In the Landau-Ginzburg picture, I will have to say I have changed the lattice, I have changed the scale slightly and the coupling constant has changed. Yeah, so that would be the difference between this, the continuum form of this, and the high energy people are always in this continuum form, unless you put it on a lattice and worry about it. Huh? But without that, it is always in the, and therefore the two get completely, I mean, sort of, if you learn one, the other comes easily. That's the. Huh. So this is the setup that, and in this setup, what we have managed is the one-dimensional icing, because it's now. So let's get the one-dimensionalizing completely out of the way, with one more point to be seen on this. So the last thing with this 1D icing is that let's go back to the transfer matrix. We calculated the transfer matrix for the one-dimensionalizing and found that it is e to the power beta j plus 2h, e to the power minus beta j, e to the power minus beta j, e to the power j minus 2h, right? Yeah. So that was the. Let me factor out a constant part, which is e to the power beta j, and look at e to the power 2 beta h, e to the power minus 2 beta j, e to the power minus 2 beta j, e to the power minus 2 beta h, right? So I have what I have done is I have just removed a constant part of this, and I'm going to focus on this T prime, which I'll call my new transfer matrix. So the T has gone to this. So T prime so what does T prime look like? Let's say I'm in a very small, so H tending to 0, small magnetic field. So this T prime, which I'll drop the prime to prevent, then is 1 plus 2 beta H, so to the lowest order, e to the power minus 2 beta j, e to the power minus 2 beta j, 1 minus 2 beta. Now this is because after all our interest primarily was in the h going to 0. That is where the critical behavior is seen. And then, I mean, the focus is going to be always on small h. And also, what will be the other focus if I'm worried about this only near criticality is that these two terms are also going to be very small, because criticality is at t equal to 0, where, I mean, this e to the power minus 2 beta j is very small. So I have so let me write this in terms of so this is equal to one 0 0 plus 2 beta h e to the power minus 2 beta j e to the power minus 2 beta j and minus 2 beta h, which is equal to 1001 plus 2 beta h into 1 e to the power minus 2 beta j e to the power minus 2 beta j minus 1, which is equal to 1001 plus 2 beta h into 1 minus 100 plus what did I do? I want to keep that as 2 beta h 1001. I've missed something. Yeah. Yes, right. Activate. Right. Sorry. It is, let me just write it in one step. 2 beta h, and it should have been 100 minus 1, and then plus e to the power minus 2 beta j 0110. Pauli matrices. So it is 1 plus 2 beta h sigma 3 plus e to the power minus 2 beta j sigma 1. Right, absolutely. So there is the decomposition. So I have stipulated that this is small and this is small. So I'm near criticality, h tending to 0, t tending to 0. And so it is near criticality, and near criticality, these are all small. These are small. Very good. If I have a Hamiltonian quantum system, the time development operator is minus IHT over H bar. So IHT over an H bar, which is the, and therefore if I go from some initial state to a final state, I would be looking at, or so if from I initial to F in steps of delta t, then it is e to the power, every step is e to the power minus IH delta t over H bar. So that is for a small step. And if it is from so from, let's say, a state initial, which is 0, you go e to the power minus IH delta t over H to an intermediate state, let's say 1, and then again another, which is like this over there over H, and to say, let's say, n e to the power minus IH delta t over H bar, and over here the final state, whatever. Right? So that's the e to the power minus IHT over this takes the 0th state going into, so it is between 0 IHT over H bar, between 0 and final, that matrix element broken up into this one through 1 1 1, yeah. So now look at, so e to the power, so one step is e to the power minus IH delta t with this, which is e to the power 1 minus IH delta t over H bar. Huh? Yes, right. No, well, yes and no. This is the generator, as you said. It takes me from time t to t plus delta t. That's the generator of the transformation. This has taken me from site I to site I plus 1. This transfer matrix has taken me in this StatMech problem from I over, from this step I to step I plus 1, which is the role of the transfer matrix. That has the structure which is, therefore, it corresponds to a quantum problem where the Hamiltonian is this. If I look at a Hamiltonian, which is 2 beta H sigma 3 plus e to the power minus 2 beta j sigma 1, then that Hamiltonian does what that Hamiltonian does in a time translation. This transfer matrix is doing that. This one-dimensional transfer matrix is doing exactly that in the space axis. So a one-dimensional StatMech problem is effectively the transfer matrix picture of a one-dimensional StatMech problem, taking you from one end to another by step by step, is equivalent to a simple quantum mechanical problem where you go from time t equal to 0 to a later time, time development being given by this Hamiltonian over here, and the analog of the Hamiltonian for the this StatMech problem is this combination through the pair. So there is the StatMech part over here, the statistical 2 beta h e to the power minus 2 beta j, and if you like it, here is the quantum part of it, the Pauli matrices through the sigma 3 and sigma. Yeah, so that is in 1D the stat-mech quantum correspondence. If it is d equal to 2, then it can't be this simple. It is not going to be quantum mechanics. Then it has to be a quantum field theory, because in the 2 dimensions, there is going to be just one time. When 2 spatial dependence becomes like quantum, one of them will have to become time, as you see over here, but the other would have to be like space, and therefore it would have to be quantum field theory in 1 plus 1 dimension, or a quantum many-body problem in 1 plus 1 dimension. Okay? So this is the right place to stop, because the next day next class I will demonstrate that if I start with a 2-dimensional Ising model, then I will get a quantum problem which is actually a many-body quantum problem, and if in some limit, the continuum version of that would have to be a Dirac equation, which is a lot of work. But at least we will certainly be able to demonstrate that this is the 2-dimensional Ising is going to look like a 1-dimensional many-body quantum system. All right. So this actually finishes everything you wanted to know about a 1-dimensional Ising model. And in the process, we had a lot of extra discussions which were not exactly planned, but at least it gives you a picture of where and what is going on. I mean, all these things are actually quite strongly related, and yeah, it's so fine. I mean, we have finished this. Next class that will start on the 2D. Oh, one more thing. Mid-sem, only mean field. Mid-sem.